Namaste children. I hope you are fine. And in the last class we have discussed what are irrational numbers and proving root 2, root 3 and some root 5 are irrational numbers by using the theorem 1.3. That is, if p is a prime number and if p divides a square, p also divides a for where a is a positive integer. Using that concept, we have proved root 2 is an irrational number. Now we are going to discuss the combination of a rational number and an irrational number. 5 minus root 3 is irrational, or 5 plus root 3, 7 minus root 3, 6 minus root 5, or 5 plus 6, like this also 5 minus root 3, or you can take the other number root 3 minus 5 also we can prove. These kind of numbers are irrational numbers. Similarly, prove that 3 root 5 is an irrational number. Rational number is 3, root 5 is an irrational number. So the combination of rational and irrational, we are going to prove the irrational numbers. So here, two types here it is said. So if it is given root 3 is irrational, if it is given root 3 is irrational, directly we can prove 5 minus root 3 is irrational. If it is not given root 3 is irrational, you have to prove first root 3 root 3 is irrational, then you should solve 5 minus root 3 is irrational. So in the last class we discussed how to prove root 2, root 3 and root 5, root 7 are irrational numbers. So we know how to prove. So in examination if they ask you prove that 5 minus root 3 is irrational, you have to prove first root 3 is irrational, then you have to prove 5 minus root 3 is irrational. Okay, if it is given prove that 5 minus root 3 is irrational where root 3 is irrational, then directly you can do it. So here we discussed already root 3 is an irrational number. Now we are going to prove 5 minus root 3 or 3 minus 5 or 6 plus root 5, 6 minus root 5 are irrational number. All those numbers we prove in a similar way. The similar concept will apply here. So here also we use contradictory method. So let us assume 5 minus root 3 is a rational number, or simply it is a rational. So if it is a rational number, it can be expressed in the form of p by q. So 5 minus root 3 is a rational number. Therefore 5 minus root 3 is equals to p by q, where q is not equals to 0 and p comma q are co-primes. P comma q are co-primes. So if they are not that is p comma q are co-primes and q is not equal to 0, therefore transpose 5 to that side, or you transpose p by q to left hand side and minus root 3 to the right hand side. That is 5 minus p by q is equals to root 3. So now rearrange. Root 3 is equals to what? 5, or simply we take here it is 5 minus p by q is equals to root 3 here. So by taking what it is LCM here we get q. So 5q minus p is equals to root 3. See in LHS p, q and 5 are integers. They are integers. Hence 5q minus p by q. 5q minus p by q is a rational number. If it is left hand side is a rational number, means definitely RHS also should be a rational number. That is 5q minus p by q is a rational number. So if LHS is a rational, then RHS is also a rational. But we know that what we know irrational. Therefore, is irrational. Therefore, what we can write? Therefore, our assumption is wrong. Assumption is wrong. What is our assumption? It is that 5 minus root 3 is rational. 5 minus root 3 is rational. We have taken as assumption. Hence 5 minus root 3 is irrational. So here what we are doing? We are taking 5 minus root 3 is a rational number, not a rational number. If it is a rational number, we can write this in the form of p by q, where q is not equal to 0 and p comma q are co-primes. So from 5 minus root 3 is equals to p by q, transpose p by q to LHS, you take minus p by q, and from LHS minus root 3 to RHS will become plus root 3. Now observe left hand side, we have 5, q and p, all are integers. Therefore this whole, that is 5q minus p by q is an integer. Means it is a, it is a rational number. If it is rational number, RHS, that is root 3 also should be rational number. But we have proved that is root 3 is irrational. Hence our assumption is wrong. Hence it is 5 minus root 3 is irrational. Like this only we will prove all the numbers like root 3 minus 5 or 6 plus root 5 or 2 plus root 7. All these sums will prove in the similar way. That is, we are taking that the given number is not a irrational number, it is a rational number, and we are proving that our assumption is wrong. Then hence we can say that 5 minus root 3 is irrational. Now similarly, the next example. Prove that 3 root 5 is irrational. That is the product of irrational and irrational is also irrational. Like 3 root 5, we can write 6 root 5, 2 root 2, 3 root 3. All these numbers will prove in the similar way. So again, what it is? So if you are taking same, let us assume 3 root 5 is rational. It is not irrational means it is rational. Therefore, it can be expressed in the form of p by q. Therefore, it can be expressed in the form of p by q, where q is not equal to 0 and p comma q are co-primes. Therefore, 3 root 5 is equals to p by q, where q is not equals to 0 and p comma q are co-primes. Co-primes means they have only one is the common factor. Now transpose 3 to the RHS. Therefore, it is multiplying 3 into root 5. When we transpose to the second, it divides. That is root 5 is equals to p divided by 3q. So this you take it as equation 1. From equation 1, so transpose 3 to the RHS, we get that is multiplied, therefore it divides. Hence you get p by 3q. That is in RHS, p, q and 3 are integers. They are integers. Therefore, what it is? P by 3q is a rational. It is a rational number. Now, if RHS is a rational, then LHS is also a rational. But it is also a rational. But what we know, what we have on the left hand side, that is LHS, root 5. But we know root 5 is irrational. Therefore, our assumption is wrong. Therefore, our assumption is wrong. What is our assumption? That is 3 root 5 is rational. irrational. So all these sums we will prove in the similar way. Hence 3 root 5 is an irrational number. That the given number we are taking that it is not an irrational. When it is not an irrational means it is irrational. So every rational number can be written in the form of p by q, where q is not equal to 0 and p comma q are co-primes, and by transposing keeping the root that is irrational number values on one side, then other values we have to shift to the other side. Then we know that p, q and the other numbers are integers, therefore the whole part will be is what? A rational number. When LHS is a rational number means definitely RHS also should be a rational number. So here RHS and our rational number is there, and LHS which is not a rational number root 5, we know that it is an irrational number. Therefore our assumption is wrong. Hence 3 root 5 is irrational. So like this we prove this 3 root 5 or any numbers like 6 root 5, 2 root 2, 3 root 5 all are irrational numbers. 3 root 3 or etc. I think, did you understand, children? I hope you understood. We will continue the next concept. Now we will discuss two theorems, that is the revisiting rational numbers and their decimal expansions. So in the previous video I explained what are rational numbers. The rational numbers which are in the form, can be expressed in the form of p by q, where p and q are integers, q is not equals to 0, and p by q form will be always the simplest form, that is the lowest form or the standard form will be there. Is there. Now, so theorem 1.5, let x be a rational number. So our topic here is revisiting rational numbers and their decimal expansions. I have explained already. Decimal expansion of rational numbers is terminating decimals, non-terminating decimals are there. In non-terminating decimals, repeating decimals are there. So terminating decimals, non-terminating, repeating decimals are rational numbers. Now we are going to discuss their properties in the form of theorems. Theorem 1.5. Let x be a rational number. X be a rational number whose decimal expansion is in the form of p by q, where p comma q are co-primes. Co-primes means again it is they have only one is the common factor, and the prime factorization of q it is denominator, is of the form 2 to the power of n into 5 to the power of m. 2 to the power of n into 5 to the power of m means they have the prime factors only 2 and 5. 2 and 5. Where n and m are non-negative integers, means they are positive integers including 0. 0 is non-negative integer. So positive integers and 0 also it is included. Now see, for example, it is 0.375. 0.375. It is a decimal number and it is a rational number. So it is the decimal expansion is in the form of p by q. So we can write this in the form of p by q as 375 by it is. So 3 digits are there after decimal point. So the denominator will get what it is? 3 zeros, that is 1000. So 0.375 is equals to 375 by 100. So it is the p by q form, but here p and q are not co-primes. P and q should be co-primes. So go for what it is cancellations. It is 5 sevens are 35, 2 with 5 25, 5 fives are 25. So 5 twos are 10, 5 zeros are 0, 5 zeros are 0. Again with 5 ones are 5, 7 minus 5 it is 2, bring 5, 25, 5 fives are 25. 5 fours are 20, 5 zeros are 0. Again 5 threes are 15, 5 eights are 40. Now what we got, it is 3 by 8. So 3 and 8 both are co-primes. The factors of 3 are 1 comma 3. Factors of 8 are 1 comma 2 comma 4 comma 8. So the common factor is only 1. Therefore 3 comma 8 are co-primes. Now this decimal number, that is a rational number which is whose decimal expansion is 0.375, can be written in the form of p by q, where p and q are it is co-primes. Q is not equal to 0. So when it is written, now the prime factorization of q, that is 8. The prime factorization of 8 is what? Prime factorization of 8. Prime factorization of 8 is what is the prime factorization of 8? It is 2 4s are 8, 2 2s are 4. That is 8 is equals to 2 into 2 into 2, that is 2 to the power of 3 we got. 2 to the power of 3. So into 1 if we write that is 2 to the power of 3 into 1, I can write it as 5 to the power of 0. 5 to the power of 0. So here the 8 can be written as what? 2 cube into 5 to the power of 0. 5 to the power of 0, how we got? 1. So any number to the power 0 is always 1 except for 0. Therefore 8 can be written as what? 8 is equals to 2 to the power of 3 into 5 to the power of 0. Now it is in the form of 2 to the power of n into 5 to the power of m, where n is equals to 3 and m is equals to 0. So these decimals are rational numbers can be expressed in the decimal expansion, whose p by q, that is they can be expressed in the form of p by q, where q is not equal to 0 and q, the prime factorization of q will be in the form of 2 to the power of n into 5 to the power of n. You take any number like this, we will get the prime factorization of the q, that is the denominator, will be in the form of 2 to the power of n and 5 to the power of m. If they contains the prime factors of the q is in the form of 2 to the power of n and 5 to the power of m, those decimals numbers are terminating decimals. Terminating decimals. You will see here it is theorem 1.6. What it states that let x is equals to p by q be a rational number such that the prime factorization of q is in the form of 2 to the power of n and into 5 to the power of m, where m comma n are non-negative integers, then x has a decimal expansion which terminates. So the terminating decimals, the rational numbers whose decimal expansion is terminated, they can be expressed in the form of p by q, where q is what it is, q is not equal to 0 and the prime factorization of q is in the form of 2 to the power of n and 5 to the into 5 to the power of m. We will see the example. So now it is 3 by 8 I have taken here. So it is in the form of what? P by q. Here q is equals to what? 8. So the prime factorization of 8 is equals to what? 2 into 2 into 2, that is equals to 2 cube. 2 cube. Even I can take 1, that is equals to 2 cube into 1, I can write it as what? 5 to the power of 0. 5 to the power of 0. 1 can be written as 5 to the power of 0 or 6 to the power of 0, 7 to the power of 0. Any number to the power of 0 is always 1. So that is the prime factorization of q is equals to what it is? 2 cube into 5 to the power of 0. It is in the form of 2 power n into 5 to the power of n. Then the decimal expansion of 3 comma, that is 3 by 8, it will be terminated. We will check it whether it is terminated or not. So divide the 3 with 8. So 3 is not divisible by 8. So we will keep point and we get 0. So 8, now it is 8 3s are 24. 30 minus 24 is 6. Then bring 0, 16. Now 8 7s are 56. 60 minus 56 is 4. Bring 0. 8 5s are 40. We got remainder is 0. Therefore, the decimal expansion of 3 by 8 is equals to what? 0.375, which is a terminating decimal. Terminating decimal. So whose decimal? Terminating decimal. Decimal. So now if that is a q number of in the p by q form, if its prime factorization is in the form of 2 to the power of n and 5 into 5 to the power of m, then that rational number decimal expansion is terminating. It terminates. An example we have discussed here. So now without doing this what it is division, we can say that the rational number will terminate or not. How? By finding the prime factorization of q, that is the denominator. If the prime factorization of q is in the form of 2 to the power of n into 5 to the power of m, then that decimal number will terminate. So which decimal numbers will be terminated for the given rational numbers? If the prime factorization of q in p by q, if it contains if the prime factorization of q is in the form of 2 to the power of n into 5 5 to the power of m, then that rational number's decimal expansion is terminated. It is terminated. If it is not in the form of 2 to the power of n into 5 to the power of m, then the decimal expansion is not terminated. It is not terminated and it is recurring, repeated. The digits will be repeated. When the digits will be repeated and it is not terminated, when the prime factorization of q is not in the form of 2 to the power of n into 5 to the power of m, then those decimal expansions will not be terminated and it is repeated. That is non-terminated repeating or non-terminated recurring decimals. That we will discuss under theorem 1.7. Is it clear? Yes. Now, theorem 1.7 states that let x is equals to b by q be a rational number such that the prime factorization of q, that is the denominator, is not of the form 2 to the power of n into 5 to the power of m, where n comma m are non-negative integers. Then x has a decimal expansion which is not terminating, repeating or recurring decimal. So here, if the prime factorization of q is not in the form of 2 to the power of n into 5 to the power of m, it means that the prime factors of q is not 2 or not, it is 5, then we can say that the decimal expansion of that rational number is non-terminating, repeating decimal. We will see some examples. We take 1 by 7. Here q is equals to what? 7. 1 by 7. Here q is equals to what it is? 7. So the prime factorization of 7 is what? 7 itself. The prime factorization of 7 is equals to 7 itself. It do not contain it is not in the form of 2 to the power of n into 5 to the power of m, or it do not contain the prime factors as 2 and 5. Therefore, the decimal expansion of 1 by 7. Therefore, the decimal expansion of 1 by 7 is what it is? Non-terminating recurring decimal or repeating decimal. Non-terminating repeating decimal. So its decimal expansion it is what? Non-terminating repeating decimal. If we divide 1 with 7, we can find out it is a non-terminating repeating decimal. Not only like this, we can take examples like 2 by 7 or 1 by 14, or it is 2 by 15, 2 by 15, 2 by 15. Like this, we can write so many examples whose decimal expansion is non-terminating repeating decimal. So which whose decimal expansion is non-terminating? If the prime factorization of q, that is denominator, is not in the form of 2 to the power of n into 5 to the power of m, then we can say that the decimal expansion is non-terminating repeating decimal. Now using these three theorems, 1.5, 1.6 and 1.7, we will solve the next exercise, that is 1.4 exercise. Is it clear, children? The theorems, the statements and with examples? Yes. Now we will discuss exercise number 1.4. First bit, without actually performing long division, state whether the following rational numbers will have a terminating decimal expansion or non-terminating repeating decimal expansion. So just now we have studied two theorems. So when a decimal expansion of a rational number will have the terminating decimal, if the prime factorization of the q factor, that is the denominator, if it is in the form of 2 to the power of n into 5 to the power of m, then the decimal expansion is terminating. Otherwise, if it is not in the form of 2 to the power of n into 5 to the power of m, then that decimal expansion is non-terminating, non-repeating, non-terminating repeating decimal, non-terminating repeating decimal. We will check out the first sum here. It is that is 13 divided by 3125. So find the first prime factorization of 3125. 3125. So it is 5 is there, the units place, therefore it is divisible by 5. 5 6 are 30, 1 with the 2 12, 5 2s are 10, 12 minus 10 it is 2, bring 5 25, 5 5s are 25. Now with the 5 1s are 5, 6 minus 5 1, bring 2 12, 5 2s are 10, 12 minus 10 it is 2, bring 5 25, 5 5s are 25. Now with 5 2s are 10, 5 5s are 25. Then it is 5 5s are 25. So the last number we got prime number. Therefore, that is 3125 can be written as what? 5 to the power 5 into 5 into 5 into 5 into 5, 5 to the power of 5 into 2 power 0. Therefore, 13 divided by 3125 is a terminating decimal. Is a terminating decimal. Why it is a terminating decimal? Because the decimal expansion of the Q factor, that is 3125, is in the form of 5 to the power of m into 2 to the power of n, or 2 to the power of n into 5 to the power of m. Therefore, it is a terminating decimal. So now we will discuss the next sum, that is the third sum. Here it is. So third sum we have 64 divided by 455. So here 455. Find the prime factors of 455. So 5 is there in the units place, therefore it is divisible by 5. 5 9s are 45 and 5 1s are 5. Then with this divisible by what? 7. 7 1s are 7. 9 minus 7 it is 2. Bring 1 21. 7 3s are 21. 13 we got. Therefore 455 is equals to 5 into 7 into 13. 5 into 7 into 13. Now the prime factorization of 455 is not of the form, what it is 5 to the power, sorry, it is not of the form 2 to the power of m into 5 to the power of m. Therefore 64 divided by 455 is non-terminating repeating decimal, non-terminating repeating decimal. So like this we can identify the given decimals, their expansions are repeating or non-repeating, the terminating decimals are non-terminating repeating decimals by finding the prime factorization of denominators. If it is in the form of 2 to the power of m into 5 to the power of m, then the decimals are terminating decimals. Otherwise they are not non-terminating repeating decimals. Is it clear? Yes? Now we will discuss the second question. Write down the decimal expansion of those rational numbers in question number 1. That is, we discuss the question number 1 above which have terminating decimal expansions. We found in the first question whose decimal expansion is terminating and whose decimal expansion is non-terminating repeating. So if it is a terminating decimal, write down the decimal expansion of the terminating decimals from the first bit. So we have done the first bit of the first bit. 13 by 3125. We have proved that it is a terminating decimal. Then what is its decimal expansion? To find the decimal expansion of any number which is in the form of p by q. So convert the denominator, that is q factor, in the form of multiples of 10. Why it is? So 10 can be written as 2 into 5. It is a terminating decimal. If it is the denominator as a 10. 100 can be written as what? 2 into 2 into 5 into 5. Even if it take 1000 can be written as 2 into 2 into 2 into 5 into 5 into 5. 5 into 5 into 5. 5 later. So the multiples of 10 we have all the prime factorization of multiples of 10 we have 2 and 5. So it is in the form of 2 to the power of n into 5 to the power of m. Then we can say that those decimal expansions are terminates. So identify the prime factorization of the denominator if it is in this form or not. If it is not in this form, we need to multiply the number which prime factor is not there. So prime factorization of 3125 we have done. It is 5 6 are 5 2s are 5 5s are we got. Then with 5 1s are 5 2s are 5 5s are. Then with 5 2s are 5 5s are. Then with 5 5s are 25 we got. That is equals to 13 divided by 5 to the power of 5. 5 to the power of 5. To get the multiple of 10, the powers of the prime factors 2 and 5, they should be equal. So here 5 to the power of 5 is there. What is the other factor it should have? 2 should be there. The power of 2 also should be equal to 5 or not. Therefore, multiply with the 2 to the power of 5 and divide with the 2 to the power of 5. That is, multiply both numerator and denominator with 2 to the power of 5. If it is 5 cube is there, multiply with 2 cube. If it is 5 to the power of 7 is there, multiply and divide with the 2 to the power of 7. To get the powers of both the prime factors 5 and 2 should be equal. Then we get the product in the denominator, that is cube factor, is in the form of multiples of 10, so that it is easy for us to convert the rational number in the decimal expansion. Now it is 13 into 2 to the power of 5 means it is 2 into 2, 4, 4 into 2, 8, 8 into 2, 16, 16 into 2 is 32. So 32 divided by, so here a power m into b power m is equals to a to the power a into b whole power m, that is 5 into 2 whole to the power of 5, that is equals to 13 into 32 divided by 5 into 2 is 10 to the power of 5, which is equals to, now multiply these two numbers. 13 2s are 26, 2 is there. 33s are 39, 39 plus 2 is 41. 416 divided by 10 to the power of 5 means it is 1 after 5 zeros on the right side. So it is 1 lakh. So when we divide with over 10, what is the decimal point? It shifts from right side to left side 1 digit, as 1 zero is there. If it is 2 zeros, it is 100. If you divide with 100, the decimal point will shift 2 places. If it is 1000, the decimal point will move 3 places from right side to left side. Here 5 zeros are there, therefore the decimal point should move 5 places. Where is the decimal point? It is 416 means 416.000. So after 6 we have decimal point is there. So it should move 5 places. We have 1, 2, 3. 4th and 5th place is not there, so we should keep 2 zeros. Therefore it is 0.00416 is the decimal expansion of 13 by 3125. So how to do here? We did not done the actual division. Prime factorization method concept we applied here. It is, that is, find the prime factors of what it is a denominator, then make the prime factors of the denominator equal with their powers of 2 and 5. For that we need to multiply and divide both numerator and denominator with the required power. Then you divide with the number which we get, the denominator will get always in the form of multiples of 10. I think you understand this, how to convert the right decimal expansion of the given terminating decimals. Now today's homework is exercise number 1.3, question number 2 and question number 3. Then exercise number 1.4, it is question number 1, question number 2 and question number 3. So this is your homework. Please complete the homework, and I hope you understand this concept. Thank you very much.